Welcome to this fascinating exploration of the Nano Battery Lifetime Paradox. Today we're going to discover how some batteries actually get better the more you use them, defying everything we thought we knew about battery degradation. Let's start with what we normally expect. Traditional batteries degrade with use. Every time you charge and discharge your phone, the battery capacity decreases slightly. Think of it like a sponge that gets worn out. The more you squeeze and release it, the less water it can hold. This is capacity fade. But why does this happen? Why do batteries lose capacity over time? First, during charging and discharging, lithium ions insert into and leave the electrode material. This causes the particles to swell and shrink, which can cause cracking. Second, the interface between the electrode and the electrolyte becomes unstable. Side reactions form resistive layers that block ion transport. Third, as particles crack, some fragments become electrically isolated. They can no longer participate in the reaction, so capacity drops. But here's where it gets interesting. Some nanostructured anodes show the opposite behavior. Their capacity actually increases with cycling. Instead of fading, the capacity climbs. This is the Nano Battery Lifetime Paradox. The device improves the more it is used. This isn't science fiction. Real materials like tin oxide nanoparticles show this behavior. Capacity can increase by 30 to 50% over hundreds of cycles. Let me give you an analogy to help understand this. Imagine a knife that gets sharper the more you use it. With use, the blade edge doesn't wear down uniformly. Instead, microscopic chipping and grinding create a finer, sharper edge geometry. Here's another analogy. Think of a dirt path through a forest. When the path is new, it's rough. There are roots, rocks, and you have to navigate around obstacles. It's slow going. But as people walk the path repeatedly, it becomes smooth. The obstacles get worn down. The route becomes optimized. The path actually becomes easier to travel. In nanoanodes, cycling is like walking that path. It smooths the routes for lithium ions, making transport easier and capacity higher. Now let's dive into the actual mechanisms. The first is particle reshaping. Volume changes during cycling don't just crack particles, they can reshape them into better geometries. Imagine a large spherical particle. As it cycles, volume expansion and contraction cause it to fracture. But at the nanoscale, these fragments don't become isolated. Instead, they form a network of smaller, interconnected particles. You might ask, why is having smaller particles better? Surface area of a sphere is 4 pi r squared. The surface area to volume ratio is 3 divided by r. As radius decreases, this ratio increases dramatically. More surface area means more sites, where lithium ions can insert into the material. More active surface equals higher capacity. Let's do a numerical estimate. Say we start with a single particle of radius 100 nanometers. The surface area is 4 pi times 100 squared, which is about 126,000 square nanometers. Now suppose this particle splits into 8 smaller particles, each with radius 50 nanometers. The total surface area is now 8 times 4 pi times 50 squared. That's about 251,000 square nanometers. The surface area doubled just by splitting into smaller pieces. The second mechanism is interface stabilization. This might seem counterintuitive because we said interfaces usually degrade. During the first few cycles, the solid electrolyte interface, or SEI layer, forms chaotically. It's thick, non-uniform, and highly resistive. Think of it like paint being applied carelessly. It's lumpy and uneven. But with continued cycling, this layer evolves. Parts that are unstable dissolve and reform. Parts that are stable remain. Eventually, you get a thin, uniform, and protective layer. Like a well-seasoned cast iron pan, the more you use it properly, the better the protective coating becomes. A better SEI layer means lower resistance to ion transport. Lower resistance means the battery can deliver higher capacity at the same current. Remember Ohm's law. The terminal voltage equals the open circuit voltage minus the current times resistance. Lower resistance means higher operating voltage, which translates to more usable capacity. The third mechanism is perhaps the most fascinating: activation of hidden storage sites. In the pristine material, Not all sites where lithium can be stored are actually accessible. Some are blocked by structural defects or poor connectivity. Think of a parking garage where some spaces are blocked by construction cones. The spaces exist, but you can't park there. As the material undergoes volume changes during cycling, the structure becomes more disordered. But this controlled disorder can actually open up new pathways. The construction cones get knocked over. Now those previously inaccessible parking spaces can be used. The garage's effective capacity increases. A concrete example is grain boundaries. In nanocrystalline materials, the boundaries between crystal grains can store lithium, but only if the structure is relaxed enough to allow insertion. Total capacity equals bulk storage plus surface storage plus interfacial storage. Initially, the interface term is small. With cycling, it grows. Let's look at a simple mathematical model that captures this capacity evolution behavior. We can model capacity as a function of cycle number n. C of n equals C0 plus A times 1 minus e to the minus n over tau minus b times n. C0 is the initial capacity when the battery is fresh. The term A times 1 minus exponential decay represents the capacity gain from activation mechanisms. It grows rapidly at first, then saturates. The term Bn represents the traditional linear capacity, fade from degradation. This is always present but can be outweighed early on. Tau is the characteristic time constant for the activation process. Smaller tau means faster activation. If we plot this, we see capacity rises initially as activation dominates, reaches a peak, then slowly declines as degradation takes over. Let's plug in some realistic numbers. Say C0 is 800 milliamp-hours per gram, A is 200, B is 0.3, and tau is 50 cycles. At cycle 100, capacity is about 956 milliamp-hours per gram. That's a 20% increase from the initial value. At cycle 500, capacity is about 850 milliamp-hours per gram, still above the initial value, but the degradation is catching up. You might wonder, if this effect is so beneficial, why don't we see it in regular, bulk electrode materials? The answer is size. These effects are fundamentally nanoscale phenomena. In bulk materials, when particles crack, the fragments are too large. They become electrically isolated, and capacity drops immediately. But in nanoparticles, even when they fragment, the pieces stay small enough to remain connected through van der Waals forces and the conductive network. The key is that the nanoscale dimension is smaller than the lithium diffusion length. This means ions can reach the center of even fragmented particles. Let's estimate the critical size below which this works. The diffusion length is the square root of the diffusion coefficient times time. For lithium and metal oxides, the diffusion coefficient is about 10 to the minus 12 centimeters squared per second. A typical charge time is 1 hour or 3,600 seconds. The diffusion length is about 60 nanometers. Particles smaller than this can be fully utilized even after fragmentation. Now let's discuss the limitations. This effect doesn't last forever, and there are trade-offs. Eventually, traditional degradation mechanisms catch up. After hundreds or thousands of cycles, capacity will decline. The effect works best at moderate charge-discharge rates. At very high rates, there's too much stress, and particles pulverize rather than reshape optimally. Not all materials exhibit this behavior. It's most pronounced in conversion and alloying anodes like metal oxides and silicon. The electrode must be designed properly. You need enough conductive additives and binder to maintain electrical connectivity as particles reshape. What are the practical implications of this discovery for battery technology? First, it challenges how we test batteries. We typically measure capacity at cycle 1 and assume it's the maximum. But for these materials, that's not true. Battery formation protocols, the initial cycles that condition the battery, need to be optimized to activate these beneficial effects. This opens the door to new electrode designs. We can intentionally use materials that will reshape beneficially rather than trying to prevent all structural changes. Paradoxically, regularly using these batteries might extend their calendar life, like a car that runs better when driven regularly versus sitting unused. Let's look at a specific real-world example. tin oxide nanoanodes. The reaction is tin oxide plus 4 lithium ions and 4 electrons gives tin metal plus lithium oxide. Then the tin can alloy with more lithium to form lithium-tin alloys, where X can be up to 4.4. The theoretical capacity for just the conversion reaction is 782 mAh per gram. With the alloying reaction, total capacity can exceed 1500 mAh per gram. That's 4 times higher than graphite. Researchers have observed that in nano-sized tin oxide, capacity rises for the first 50 to 200 cycles, often reaching values well above the initial discharge. After many cycles, the material transforms into a composite of tin nanoparticles embedded in a lithium oxide matrix. This nanocomposite is actually more electrochemically active than the original material. This behavior is also seen in silicon anodes, which are being developed for next-generation lithium-ion batteries. Silicon alloys with lithium according to this reaction, where X can be up to 4.4. The problem is, silicon expands by 300% during lithiation. This causes massive mechanical stress. But nano-sized silicon particles can accommodate this expansion without catastrophic failure. The particles can expand into surrounding space. For silicon, capacity typically peaks around cycle 20 to 50 as the material pulverizes into an optimal nanostructure. Let me give you one final analogy that ties everything together. Think of these nanoanodes like muscles. When you first start exercising, your muscles are sore and weak. The initial workout causes microscopic damage. But with continued training, the muscles don't just heal, they adapt. They become stronger, more efficient, and better at the task. The initial damage triggers a remodeling process that makes the tissue better suited to the stress it's experiencing. Nanoanodes work the same way. The stress of cycling triggers structural remodeling that optimizes the material for charge storage. Let's summarize the key concepts we've covered. The Nano Battery Lifetime Paradox is that some nanostructured anodes actually improve with cycling rather than degrading. 3 main mechanisms drive this: particle reshaping that increases surface area, interface stabilization that reduces resistance, and activation of hidden storage sites. This phenomenon only occurs at the nanoscale, typically for particles below 100 nanometers, because that's where beneficial restructuring outweighs catastrophic failure. The effect is temporary, lasting for tens to hundreds of cycles, but the capacity gains can be 20 to 50%, which is significant. We can model this with an equation that includes both activation and degradation terms, capturing the rise and eventual fall in capacity. What does this tell us about materials science and engineering more broadly? It teaches us that wear and damage are not always purely destructive. Under the right conditions, they can lead to improved performance. It reinforces that nanoscale materials behave fundamentally differently from bulk materials. Size really does matter. It suggests we should design materials not just for durability, but for beneficial adaptation. Allow controlled evolution, rather than trying to prevent all change. This is actually a principle nature uses extensively. Bone remodels under stress to become stronger. Neural pathways strengthen with use. Living systems improve through use, not in spite of it. Where is this research heading? Researchers are now trying to design materials that intentionally self-optimize during operation, materials that evolve toward their ideal structure. Advanced microscopy and computation are revealing the atomic scale mechanisms of this transformation, allowing us to enhance the effects. The principles are being extended beyond lithium-ion to sodium-ion, magnesium batteries, and even supercapacitors. Here's a final thought to leave you with. In materials science, we often strive for perfect, defect-free structures, but this research shows that perfection is not always the pristine state. Sometimes the best structure is one that emerges through use, shaped by the very stresses it will encounter in operation. At the nanoscale, wear can act like renewal. Degradation can lead to improvement, and a device can become better the more it is used.